Hello, in this video we're going to begin our description of acids and bases by remembering our definitions and adding some new definitions as to exactly what acids and bases are. So we're here in section 20.1. So, classification. How do we define acids and bases? And then from here we'll go throughout the rest of the chapter talking about equilibria and things about acids and bases. So again, our definition, before, in this course at least, we only gave you the Arrhenius definition of an acid and a base. And so this is defined in water that an acid produces H3O+ when dissolved in water, and a base produces OH- when dissolved in water. Now let me talk about H3O+ for a second, is that we chemists are often pretty lazy, where we should say H3O+, hydronium ion, because that really is what exists in solution. But often we just say H+ instead because we're lazy. And H+ is really just a proton, and a proton is too small to exist just by itself in aqueous solution without interacting with the water, right? So we say H+, really it's hydronium ion. So sometimes you'll see reactions written like they are up top, and this one's the better one, ta-da! But you can also write this very same reaction as hydrochloric acid is in equilibrium with H+ and Cl-. And it's just a shorter way to write it. Really, it means the same thing. You're just adding or subtracting water to both sides, in effect. When I first started teaching, I used this shorter method. But then I realized, if I'm going to do this, I might as well do it right. And so now I give this method. But just keep in mind that you'll still see both of these very commonly. Okay, so that's the Arrhenius acid. Then an Arrhenius base produces hydroxide anion when it's dissolved in water. So sodium hydroxide produces Na+, OH-. So then in the Arrhenius definition, when we talk about a neutralization reaction, which is a reaction between an acid and a base, in effect we're saying, well, since the acid produces H3O+, it reacts with the base, which produces OH-, and this makes water. In reality, you put HCl in, which that makes the H3O+. You put sodium hydroxide in, that makes the OH-, right? And then you get water and a salt. But really, it's the hydronium and the hydroxide ions that are reacting together to make the water in the Arrhenius theory. And that works for a lot of systems and it's pretty simple, so we still use it a lot. However, it does have some problems, right? Ammonia, when you put it in water, is basic, the NH3. And how is it basic? It doesn't contain an OH ion to release to the water. Sodium carbonate, sodium oxide are also basic, but they don't have hydroxide ions. When you dissolve carbon dioxide into water, it's a little acidic, which you might notice that if you ever drink a carbonated versus flat beverage. And that does not contain hydrogen ions to release, right? And then acid-base chemistry at times also works when you're not in aqueous solution, and this doesn't explain how that would work. So we need some new definitions. So we have the Brønsted-Lowry definition, and we have the Lewis definition that we'll add into our repertoire today. So here's the Brønsted-Lowry definition. A little broader. So here, the acid can donate a hydrogen ion, so it donates H+. And since hydrogen +1 is really just a proton with no neutron or electron, we call this a proton donor. So, okay, so the acid can donate protons, then the base can accept protons. So here's an example down here. We have acetic acid, and acetic acid is written this way to show that this hydrogen right here is the one that can be donated, whereas these hydrogens here don't get donated at all. So, looking at this reaction, let's define the acids and bases. So the acetic acid on the left, I mean, its name is kind of a giveaway. What it does is it donates that hydrogen to the water. And so then the water in this side of the reaction on the left acts like a base because it accepts that hydrogen ion. And then it forms H3O+, hydronium, and the acetic acid negative ion version, which is called acetate. Now, this reverse reaction also works. In the reverse reaction, the hydronium ion donates one of its hydrogens back to the acetate ion. And in this case, the hydronium ion is functioning like an acid, and then the acetate ion is actually functioning like a base. And so we actually use this as part of our definition. We call them conjugate acids and bases. So here, this is the acid, and then this is its conjugate base. And it kind of makes sense. Hey, I have the same bulk of the molecule, whether it has the hydrogen on there or not, makes it an acid or a base, but it's overall the same hunk of molecule. And then here, this is the base, and here's its conjugate acid. But since water does this all the time, and it's often one of the pairs in a reaction, it doesn't get the glory it needs, so we often just talk about the other part. In this case, the acetic acid and acetate. So to formalize this a little bit, here's another example and a description. So a conjugate acid-base pairs is the acid and the base that's formed after you donate that proton, or the base and the acid that's formed after it accepts that proton. And we talk about this in more detail later in this chapter, but we're going to introduce it here because it makes sense as part of the definition. And then, hey, if you hear it twice, awesome. So for this reaction down here, we have ammonia, NH3, and water reacting together. So ammonia is the base because the base is going to accept a proton that comes from water. So one of these hydrogen ions on water comes down and lands on this ammonia. So this goes this way. And so the base is a proton acceptor. The water is the proton donor, so that makes the water the acid, the ammonia the base. And then now, the ammonia is NH4+, because it accepted that proton, which then, ammonium, NH4+, can function like an acid. It can take this proton, donate it back to the base, and ta-da, right? So, this is the base, this is its conjugate acid, this is one acid-base conjugate pair, and then water and hydroxide is the other. Again, we'll talk about this more thoroughly later, but wanted to introduce it here now. One other thing we should talk about is amphoteric ions or molecules, and those can either accept or donate a hydrogen ion. So bicarbonate is an example of this. It can either donate or accept a hydrogen ion. It can even do that with itself. So two bicarbonate molecules, one can function as the acid, one as the base, and they'll transfer that hydrogen ion to make carbonate, CO3 2-, and carbonic acid, H2CO3. And then this happens when you put baking soda in your cookies that you're making. Baking soda is sodium bicarbonate, HCO3, and it'll react with itself. It'll make H2CO3, and then this carbonic acid makes CO2 and water. And hey, that CO2 is what leavens your cookies or your bread or whatever it is you're making. All right, last definition to include Lewis acids and bases. So this is Lewis as in Lewis structure. So we're talking about Lewis structures. And so BF3 is a Lewis acid. And we define it here as it can accept an electron pair. Remember, an acid is a proton donor, but it accepts an electron pair. Whereas a base accepts a proton, and in doing so, it donates an electron pair. So we can use this electron pair definition to talk about acids and bases as well. So let's do that. So in one of the previous slides, we had H+ working with NH3 to make ammonium, NH4+, and NH3 was the base, H3O+ or H2O or whatever was the acid. And so I'll just simplify this as H+ for the moment. And all right, so you have these together, and then you're going to make a reaction where the electrons here donate into this bond. And so instead of having electrons here, now you have a nice bond. And so that's what it means by donating an electron pair. Those electrons that are a lone pair on the NH3 turn into the bond between NH3 and that hydrogen. And this is no longer positive. And then a Lewis acid can accept an electron pair. So if you had, say, hydroxide, and it has an electron pair sitting here, actually has a couple electron pairs, this electron pair can donate onto this BF3, and it can make a nice bond. So these electrons get donated, and then it makes a nice bond like this. And I really need to work on making my stuff look prettier. Hello. Now you can have a neutralization reaction in this formalism as well. The Lewis acid and the Lewis base come together, the lone pair on the nitrogen makes this bond between the acid and the base, and you make a molecule. And so this definition does not require water at all, which is kind of nice. So this would work in organic solvents or some other places where you don't have water. It's just a more specific definition of acids and bases. But there's a lot of times when we don't need this precision or this specificity, and we can get away with one of the other two models that we talked about before because they're simpler or easy to think about. Great, that's what we have for this video. Thanks for watching.